Right, good day. Welcome to this video on complex analysis. In a bit to try and finish this course due to the lockdown. Right, I'm going to continue from where we left, and I think the next part was to look at real integrals. Right, this is for course SMAR 2201, complex analysis. And the part that I'm going to look at is evaluation of real integral. Evaluation of real integrals. That is using complex analysis. Right, I'm going to look at this by means of two examples. That is to say, if we are given an integral of the form minus infinity to infinity of f of x dx, right? How do we evaluate this integral? And the standard form is integral. Say, let me have this as an example here. Example 1. Evaluate the integral from minus infinity to infinity of what? Of dx over x to the 6 plus 1 per se. And note that these are integrals from minus infinity to infinity over dx over 1 plus x to the power 2n for some integer n. I'm not going to consider the case when n, or I'm not going to consider the cases integral from this from minus infinity to infinity of dx over 1 plus x to the power 2n plus 1. When this power here is odd, we're only going to stick to those powers. This here is outside the scope of this course. Maybe I can do as an aside out of interest, but for the purposes of this course, we're only going to stick to integrals of this form. And as an example, I'm going to consider this integral here. And as we discussed before the lockdown, we said you consider the auxiliary integral I, which is given by the integral around c of dz over z to the 6 plus 1, where c is the path given by the semicircle from minus infinity up to infinity, x and y. Right. And we consider poles. We consider poles that are in the upper half plane. That is poles along the line y equal to 0. Anything that is greater than y equal to 0, that is poles that are in this region for this diagram here. And we know that we have poles whenever when the denominator is equal to 0, so that is to say when z to the 6 is equal to minus 1. And the other way, or I can rewrite this now as z to the power 6 equal to e to the I 2k plus 1 by pi using Euler's formula. Minus 1, I can replace it with that, so that I end up with what? I end up with z is equal to e to the I 2k plus 1 by pi over 6. Right, then I consider different values of k, because here I'm taking k to be integers. Right, that is to say, define z naught. That is the case when k is equal to 0. I'm going to get what? Z naught is going to be given by e to the I pi over 6. Z1 is going to be given by what? By e to the I pi over 2. And Z2 is given by what? E to the I 5 pi over 6 Z 3 is given by e to the I 7 pi over 6 z4 is given by what? E to the I 9 pi over 6, and then your z5 is given by e to the I 11 pi over 6. Then ideally I can go on beyond k equal to 6, because when k equal to 6, I get my z6, which is given by what? E to the I 13 pi over 6. But 13, this thing I can rewrite as e to the I 12 plus 1 pi over 6, which is equal to e to the I 12 pi over 6 times e to the I pi over 6. And this is nothing but e to the I 2 pi times e to the I pi over 6. And we know this thing here is equal to 1. So that my z6 is equal to e to the I pi over 6, which is the same as z0. So you can see that there are 6 unique poles. That is z0 up to z5. z6 is just nothing but z0. z7 will be nothing but z1, on and on. So there are 6 unique poles, that is z0 up to z5. And we only consider the poles of those that are in the upper half plane. And for this problem here, the only poles in the upper half plane are z0, z1, and z2. So we are going to evaluate the residue of these points. That is to say, residue of f evaluated at z0. This is given by what? By the limit as z goes to z0 of z minus z0 over z 6 plus 1. And then this by L'Hopital's rule becomes what? This is nothing but the limit as z approaches z0 of 1 over 6 by z to the 5. And if I evaluate this limit here, this is equal to 1 over 6 by z to the minus 5. And this is equal to, this residue becomes 1 over 6 times this raised to the minus 5. This becomes e to the minus I 5 pi over 6. So that's residue for z0. Right, so res of f at z0 is given by 1 over 6 e to the minus I 5 pi over 6, and then the residue of f at z1, nothing much changes except that I'm replacing z0 with z1, and then the limit as this goes to that. So I'll end up with 1 over 6 to the by 5 to the minus by z by to the power minus 5, and I'm simply substituting this here. So I'll end up with this residue being what? Being e 1 over 6 e to the minus I 5 pi over 2, but this one here is nothing but e to the minus I pi over 2. And then the residue of f at z2 is nothing but 1 over 6 by e to the minus I pi over 6. so that our I is equal to 2 pi I multiplied by the sum of these residues, by sum from k equal to 1 and k equal to 0 up to 2 of res of f zk. And then this is given by what? E to the minus 5 over 6. That's what. Let me pause this a little bit here.